Hi friends, in this video we are going to discuss some of the questions, but before that you need to know a few things. For example, we discussed in the quantum numbers, there is one quantum number which is known as S and it is called spin quantum number. Okay, there is M which is called as magnetic quantum number. There is L which is called as azimuthal quantum number. Okay, so spin quantum number, it just gives us the spin of an electron, which is plus half or minus half. Okay, magnetic quantum number, it gives us the magnetic moment of an electron. Okay, or the orientation of the orbital, as you can say, but mainly it gives us the information about the magnetic moment of an electron. And the spin only magnetic moment of an electron is spin only magnetic moment of an atom is mu equals under root n into n plus. Okay, where n is the number of unpaired electrons. And its unit is mu b, which is called as Bohr magneton. Okay, so what is this Bohr magneton? You do not need to go into it currently. This is not in the scope of the syllabus. So this is represented as Bm, which is the abbreviated form of Bohr magneton. Okay, so for example, in case of chromium, which is 24, the total number of unpaired electrons is 5. The total number of unpaired electrons is 6 in fact, not 5, because the outermost electronic configuration is 3d5 4s1, and if we draw the 3d5 orbitals, this is 3d5 and this is 4s1. Okay, so the electrons, all the electrons are unpaired. Okay, so in this case mu will be under root, which is 6 unpaired electrons are there, so therefore it will be under root 6 into 8, or mu will be under root 48 Bohr magneton. Okay, so in this way we calculate the number, we calculate the Bohr magneton of an atom, or the spin only magnetic moment of an atom. Okay, so in order to calculate it, first please draw the electronic configuration. Okay, and while drawing the electronic configuration, do show the total number of orbitals and clearly show the total number of unpaired electrons, because there is a high chance of doing silly mistakes in this case. Okay, now the another thing is that we know that L gives us the orbital angular momentum of an atom. Okay, so here orbital angular momentum is orbital angular momentum of an electron is h upon 2 pi under root L into L plus 1, or it is also written as h crossing L into L plus 1. This equation is very important for higher class chemistry. So in this case you do not need to go further into this equation. Just know that orbital angular momentum of an electron is represented by h upon 2 pi into L plus 1. Fine. So L here is 0 for S, 1 for P, 2 for D, 3 for F, and so on. Okay, so now let's discuss some questions based on this chapter. The question number 1, it says that the circumference of first Bohr orbit in hydrogen atom is 3.322 into 10 raised to the power minus 10 meter. What is the velocity of electrons in this orbit? Okay, so this is the question here. The circumference of first Bohr orbit in hydrogen atom is 3.322 into 10 raised to the power minus 10 meter. What is the velocity of an electron in this orbit? So here we are going to make use of a simple formula, which is mvr equals nh upon 2 pi. Fine. So this is one of the Bohr's postulate as we discussed earlier in one of the videos. So we can rearrange it as v equals nh upon 2 pi r into m. Fine. So here 2 pi r is nothing but the circumference. Okay. And the first Bohr orbit, since this is the case of first Bohr orbit, therefore n will be equal to 1. So velocity will be equal to 1 into 6.626 into 10 raised to the power minus 34 joule second divided by 3.322 into 10 raised to the power minus 10 meter into 9.1 into 10 raised to the power minus 31 kilogram, as we know that this is the mass of an electron. So if we solve it completely, then we will get the answer as velocity is equals 2.19 into 10 raised to the power minus into 10 raised to the power 8 meter per second into 10 raised to the power 6. This is 6. Okay. So this is the answer in this case. So very easy question it was. You just need to make use of the first postulate of Bohr's model and then just rearrange it and substitute the value of circumference. The rest of the things are constant. Okay. Now let's see another question. The second question says that calculate the energy emitted when electrons of 1 gram atom of hydrogen undergo transition giving the spectral lines of lowest energy lowest energy in the visible region. In the visible region of its atomic spectra. Okay, so it is asking us to calculate the energy which is emitted when electrons of 1 gram atom of hydrogen, it means 1 mole of hydrogen, undergo transition, giving the spectral lines of lowest energy in the visible region of its atomic spectra. Since we know that this spectra lies in the visible region, since it lies in visible region, we are talking about Balmer series. Okay. Okay. So therefore, here in this case, N1 equals 2, because Balmer series lies in the visible region. So N1 equals to 2, and since the lowest energy is concerned over here, and since lowest energy is given, so therefore N1 equals to 2 and N2 equals to 3, because the lowest energy corresponds to the very next level from N1. So very next level from N1 equals to 2, here is N2 equals 3. Okay, so here in this case, what we are going to do is that we are going to take the value of Rydberg's constant as 1.1 into 10 raised to the power 7 per meter. Okay, and we are going to take the value of speed of light as 3 into 10 raised to the power 8 meter per second. And also one more thing is given, which is h, Planck's constant, is 6.62 into 10 raised to the power minus 34 joule second. Okay, so now we are just supposed to make only we are just supposed to use only one formula, which is the formula for line spectrum of hydrogen, and we know that in that case 1 upon lambda equals RH 1 upon N1 square minus 1 upon N2 square. Okay, so this is going to be in per meter. So if we substitute the value, this will become 1.1 into 10 raised to the power 7 upon 1 upon 4 minus 1 upon 9. Okay, so this after solving this, the value of lambda, which comes out to be, after solving all these, after solving this particular equation, the value of lambda comes out to be 6.55 into 10 raised to the power minus 7 meter. Okay, so now, so from here the energy, if we substitute here, so if we substitute E equals hc upon lambda, so now we need to substitute the value of lambda in this equation. So this will come out to be 6.26 into 10 raised to 6.626, or here in this question it is given that take the value of h as 6.62 into 10 raised to the power minus 34 joule second into 3 into 10 raised to the power 8 meter per second divided by 6.55 into 10 raised to the power minus 7 meter. Okay, so if we solve it completely, then the value of energy which comes is 3.037 into 10 raised to the power minus 19 joule. Okay, so this is the value of energy which is calculated here. But this is the energy for one atom. And in the question we are asked to calculate the energy of 1 gram atom, which means 1 mole. So therefore total energy is E into Na. Na is the Avogadro number. So if we solve the total energy, then the answer which will come out to be is 3.037 into 10 raised to the power minus 19 into 6.023 into 10 raised to the power 23 joules. Okay, so the total energy which comes out to be after solution is almost equal to 182.5 kilojoules. Okay, so this is the answer. Fine. So now let's move on to another question. The question says the dissociation of O2 into two normal atoms requires 498 kilojoule per mole. Okay. Now oxygen also undergoes photochemical. Oxygen also undergoes photochemical dissociation into one normal atom and one excited atom having 1.967 electron volt more energy than normal atom. What is the maximum wavelength effective for photochemical dissociation of O2. Okay, so this is the question that is asked here. The dissociation of O2 into two normal atoms requires 498 kilojoule per mole. Oxygen also undergoes photochemical dissociation into one normal atom and one excited atom having 1.967 electron volt more energy than normal atom. What is the maximum wavelength effective for photochemical dissociation of O2? This particular question is very easy. In this question you just need to calculate the total energy per molecule of oxygen that is required and then equate it to Hc upon lambda. Okay, so this here what is happening is that O2 is undergoing dissociation first to 2O and then it further undergoes dissociation like this. Okay, here this is the excited atom of oxygen. Fine. So here energy E1 is required and here energy E2 is required. Okay, so now here therefore total energy, which is E, equals E1 plus E2. Now E1 is 498 kilojoule per mole. So let's convert it joule and per molecule. So in order to convert kilojoule per mole to kilojoule per molecule, we need to divide it by Avogadro number, which is 6.023 into 10 raised to the power minus into 10 raised to the power 23. Okay. So this is E1 and plus E2. E2 is nothing but 1.967. Since it is given in electron volt, we need to convert it in joule. So in order to convert electron volt to joule, we need to multiply it by 1.6 into 10 raised to the power minus 19. This is in joule. Okay. And this is nothing but Hc upon lambda. Fine. So if we solve it further, so if we substitute the value of total energy to particular this expression, so from this we will get lambda equals Hc upon E, which is 6.626 into 10 raised to the power minus 34 joule second into 3 into 10 raised to the power 8 meter per second divided by 498 into 10 raised to the power 3 upon 6.023 into 10 raised to the power 23 plus 1.967 into 1.6 into 10 raised to the power minus 19 joule. Okay, so from here the value of lambda that comes out to be is 1.7413 into 10 raised to the power minus 7 meter. This is the answer here. Okay, so if we convert it, it comes out to be 1741.3 angstrom. So if we convert meter to angstrom, the correct answer becomes this. This is the only thing that was asked in this particular problem. Okay, so now let's see one more question. So the question, it says positronium consists of an electron and a positron. In this case, mass of positron is equal to the mass of electron, but the charge is opposite. Okay, we'll see it later. Orbiting around their common center of mass. Okay, the spectrum is therefore expected. The spectrum is therefore expected to be hydrogen-like. The difference arising from mass difference. Okay. Calculate the wave number of first 3 Balmer series of positronium. Okay. Now here, the one thing that we need to know about it is that the positron contains, suppose MPO is the mass of positron, it has the mass almost equal to that of an electron. Okay. But the charge of positron is +1 unit, whereas the charge of an electron is -1 unit. Now, since in this case masses are comparable, since masses are comparable, therefore we cannot neglect any of them. Okay, so we need to take into account both of the masses. Now in this case, we take the reduced mass instead of solving them separately. We solve them in one go only, but we take the reduced mass. So therefore, reduced mass, which is mu, equals m1 m2 upon m1 plus m2. We know that for two bodies, reduced mass is m1 m2 upon m1 plus m2, because it comes from the fact that 1 upon mu equals 1 upon m1 plus 1 upon m2. Okay, so now since in this case both the masses are comparable, therefore it will come out to be m upon 2, where m is the mass of an electron or the positron. Okay, so now since we have solved up to here, and we know that RH, which is Rydberg constant, is 2 pi square m e raised to the power 4 k square upon h cube c. Okay, this is the Rydberg constant in case of an electron. Okay, when we consider the electronic spectrum. But in this case, since we are considering the reduced mass, in case of positronium, it comes out to be 2 pi square mu e raised to the power 4 k square upon h cube into c. Now, since the difference lies only in masses, okay, and mu is equal to m by 2, therefore it comes out to be RH upon 2. So therefore the Rydberg constant for hydrogen, like for hydrogen atom, is this, and the Rydberg constant for this positronium is R upon 2. R for hydrogen, Rydberg constant for hydrogen divided by 2. Okay, so now there is almost nothing left. So the only catch that was there in this problem was to calculate the Rydberg mass, Rydberg constant separately by taking reduced mass. Okay, now everything is very simple. So R positronium becomes 109,766 upon 2, or this is 109677. You can write it as 1.1 into 10 raised to the power 7 upon 2 in case of meter, per meter. Okay, this was in case of this was in centimeter per centimeter, this is in per meter. Okay, so now in case of Balmer series, the first line is n1 equals 2, n2 equals 3. Okay, so the first line that comes out to be n1 equals 2, n2 equals 3. So therefore, wave number, that is 1 upon lambda 1, or wave number 1 is 1.1 into 10 raised to the power 7 upon 2, 1 upon 4 minus 1 upon 9. Okay, so if we solve it further, then the value comes out to be almost equal to 7620 per meter. Okay, it comes out to be 7620 per centimeter. This is per centimeter. Okay, so this is for the first line, and for second line, this is 1.1 into 10 raised to the power 7 upon 2, 1 upon 4 minus 1 upon 16. Okay, so because here this is per meter, here in this case n1 equals to 2 and n2 equals 4. Okay, and for third line, that is nu bar 3, is 1.1 into 10 raised to the power 7 upon 2, 1 upon 4 minus 1 upon 25 per meter. In this case, n1 equals to 2 and n2 equals 5. Okay, so this is the respective answers for this particular problem. The only catch was there to calculate the Rydberg constant separately for positronium. Okay, and you must know the differences in masses and electric charge of electron and positron. Okay, so this was the solution of this particular problem. Okay, so now we'll see one last question. The circumference of second Bohr orbit of electron in hydrogen atom is 600 nanometer. Calculate the potential difference. Calculate the potential difference to which the electron has to be subjected so that the electron stops. Okay? The electron has the de Broglie wavelength corresponding to this circumference. Okay, so in this case, here one thing that we need to know is that we need to calculate the total energy, and then we need to we need to apply some potential difference so that the electron stops. Now we need to just make the velocity of an electron to be 0. Now since it has some kinetic energy, therefore the potential difference must be applied corresponding to the kinetic energy of this particular electron. So here in this case we know that mvr equals nh upon 2 pi. Okay, we know that mvr equals nh upon 2 pi. Okay, this comes from the Bohr's postulate. So from here, now since it has the de Broglie wavelength, so we know that lambda equals h upon mv. Okay, so now we can write it as 2 pi r equals nh upon mv. Fine, this comes out to be, this becomes, since h upon mv is lambda, so this becomes n lambda. Okay, so we know that the circumference is 2 pi r, which is given to be as 600 nanometer, and we know the value of n also. Okay, so from here lambda becomes 2 pi r upon n. So lambda comes out to be 600 into 10 raised to the power minus 9 meter upon 2, which is 300 nanometer. Okay, and so from here velocity is h upon m lambda. Okay, so therefore kinetic energy becomes, so from here kinetic energy, we know that therefore kinetic energy becomes half mv square. So it comes out to be half m into h upon m lambda square. So this becomes half into h square upon m lambda square. Okay, so kinetic energy is, so lambda is 300 nanometer. Okay, so now from here the kinetic energy that comes out to be is, kinetic energy is half h square upon m lambda square. Okay, so now if we are applying some electric field to this particular electron, then the potential difference and energy relation will be like this. Kinetic energy will be equal to E into V naught, where E is the charge of an electron, V naught is the potential difference that is applied, okay, to which the electron has been subjected. Fine. So from here V naught, that is the potential difference, it comes out to be half into h squared upon m lambda square into E. Okay, now substituting all values, we get V naught as 6.626 to 10 raised to the power minus 34 square joule square second square divided by 2 into 9.1 into 10 raised to the power minus 31 kilogram into 300 into 10 raised to the power minus 9 meter of whole square into 1.6 into 10 raised to the power minus 19 coulomb. Okay, so we have substituted all the values over here, and the value of lambda that comes out to be from all this, the value of V naught, that is potential, that comes out to be from all this is 1.675 into 10 raised to the power minus 5 volt. Okay, so this is the potential difference to which the electron has to be subjected so that the electron will stop. corresponding to the hydrogen atom in second Bohr's orbit whose circumference is 600 nanometer. Okay, so this is the answer for this particular question. So we are going to stop here for this video. In our next video we are going to discuss the JEE questions.